I'm Justina Brown.
I'm Joseph Carey.
I'm Ajani Burton.
I'm Nikai Gibson.
I'm Cameron Wright.
Starting off with this presentation, we're going to talk about our motivation. Basically, for the motivation, what motivated us to want to do this project is the fact that there are a lot of commercial businesses that have HVAC systems. Now, most of these HVAC systems come equipped with a programmable thermostat, but sometimes there are malfunctions in the programmable thermostat. So we want to create a device that can detect when there are malfunctions within the programming of the programmable thermostat. Also, another thing to look at is, although most HVAC systems come with a programmable thermostat and they come with an economizer, there are still malfunctions with the economizer also. Because there are statistics that show that although most companies have their buildings come equipped with an HVAC system that's supposed to save energy and save them money, in actuality, it actually costs them more money. So the system could also help them save more money by detecting the malfunctions and of the programmable thermostat and of the economizer.
To begin our research with trying to help design our product, we began researching data loggers. Data loggers are devices that can run alone, but they are connected to other devices to record the behavior of those host systems. Data loggers can also send out information to the customer about certain behaviors, and this will ultimately help us to try to fix this problem. So, with that being said, the next slide is just an overview of what we'll be discussing further in this presentation, starting with the engineering and marketing requirements.
There are several different requirements that are necessary to look at the solution of solving this problem. One such requirement is looking at exactly what the dimensions should be. For example, our product needs to be able to be in the 8 by 6 by 4 inches frame, so that way it's portable so that the user can easily carry it up to the HVAC system when necessary. Another major factor in our engineering requirements is the cost. The product should be very low cost and should not exceed $250 for the user. And also another major requirement is weight, which will allow the user to easily carry the product and utilize the product. We require our products to be no more than 5 ounces. And then also, in addition to that, it must be very accurate when detecting things such as current and temperature outside, so it can be able to tell when something is out of normal.
A couple of other marketing requirements, like I said, it should be hourly accurate. So with that, like I said, it has the weekly self-test. It also should be able to withstand certain conditions, whether it be weather or the actual atmosphere of where the product's going to be at. Like we said, it's going to be on the HVAC system, so most HVAC systems are on the roof, or within the actual ceiling, the ceiling and the actual roof and whatnot. So what we're striving for is just for IP, which is ingress protection, 6.7 rating, which is known as the highest rating for the actual certification of a product. And that rating pretty much shows that this product is able to withstand being in a certain environment. So like we said, we have an outdoor sensor. We have that's supposed to read the temperature. We also, like we said, we're putting this on the roof. So with that product, it has to be able to withstand certain amounts of water, whether it has to be waterproof, it has to withstand certain amounts of dust, whether it's windproof and whatnot. So that's, so next slide. The level 0 diagram, pretty much the idea of the product that we had in mind was simply it had a power source, of course. It would have the input from the sensors, and it would have the user control, which pretty much puts out the setting for the actual product. And then what it will do is send out a signal to the customer whenever the sensor goes off, which pretty much is a detection system.
Next, we have our level 1 diagram. Basically, with our level 1 diagram, we broke down how we want the system to work. We want the user to be able to program the actual device that we are making. The user can input the time, the day, how many hours, and they can also put what they want it to sense or what they don't want it to sense. Basically, from what the user inputs, that goes from the user controls go into the user configuration interface. And then from there, it goes into the control interface. And connected to the control interface are the sensors. The sensors which will detect if there's a malfunction in the system, and if the program, if the HVAC system is running when it shouldn't be running. And then from there, it will be sent to the wireless communication interface. And basically what the wireless communication interface should do is it should be able to send out alert by email or text message to the user to notify them of any malfunctions or any errors or anything that may be wrong with the HVAC system.
Just give a general overview with the level 1 diagram of the product itself. We're pretty much going to be using a basic Arduino board, and we're going to be attaching temperature sensors and a Wi-Fi shield, pretty much for the reasons that we just explained. Temperature sensor to read the temperature and compare it from the outside to the inside of the actual building, and the Wi-Fi shield in order to send a proper message to the customer. So moving on to the next slide, we have a level 2 diagram, and that was of the wireless interface system. Pretty much the outline of the system is similar to that of a modem, but like we said, we're using Arduino Shield. We're trying to do everything from the ground up. What the interface system would conceive of would pretty much be a source encoder, which would take the source information from the readings and whatnot from the temperature sensor, the comparison and whatnot, and turn it into a binary code. The binary code pretty much will be sent to the channel encoder. Channel encoder ensures that the actual code is turned into an analog signal. Now with that, we try to compress the data in order to ensure that it gets there in a reasonable amount of time, as well as it's not so much of a workload on the actual device. And then of course it will turn into a signal waveform and be sent to the actual user.
Okay, so what we did in the UML diagram is pretty much explaining and showing the relationships between our system and the different variables that we'll be controlling and being used in our system. So what we have is we'll have our temperature sensor as well as our vibration sensor coming from the commercial building to let us know if the system's running, if it's on, and the different variables of temperature and seeing if the economizer is on. As well as the user is going to be using the control interface, pretty much seeing the data loggers info and data and just seeing how everything is working and everything is working properly. And that will also be powered by our power source, which we're using a battery for. The battery will also be powering our wireless communications system, which is going to be our Wi-Fi shield, which we're going to tie onto our Arduino board. We're going to be using some kind of communication, whether it be GSM or SMS, to contact the business owner or the operator to let him know whether there's something malfunctioning, if the economizer is running when it shouldn't be, the temperature is a certain temperature, and certain time delays within the restrictions of the temperature and the system is actually working.
We have a work breakdown structure, which is generally pretty much an idea of a timeline at how the product is actually going to be built from the ground up. What's incorporated within the work breakdown structure is pretty much, like I said, it gives roles to the people who are supposed to do exactly what's what in the actual project. Myself and Ajni are more so into the circuit design, so we'll be actually purchasing the components, the Wi-Fi shield and the temperature sensors, and putting them onto the Arduino board. whereas Justina, Cameron, and Kyle will be more so into the coding basis, which creating the actual programs that will read these temperature readings and give the signal out to the home.
It's small on the slides if you wanted to take a
Thank you.
look. So,
If you notice on the actual timeline, between the actual planning process that started out in September, between now and January is more so the planning process of us actually getting an idea of what exactly needs to be put onto this product. Coming in January, we'll be buying the actual products and putting them together and testing from them. So,
Next, we had the test document, which we created. We created a test document for the sensor that's supposed to detect the temperature sensor. Basically, we wrote down, we made the test document, and we put in the test document what we wanted to test as far as what we wanted the temperature sensor to do. Right now, we're just in the beginning stage, as far as we're just testing out the temperature sensor to see what all it is capable of. So we want to test how it detects the temperatures outside for a certain time interval, and then from there we want to compare it to the temperatures outside from using just a regular outdoor temperature. Thermometer.
dealing with project management is very, very important. So with this, we also created a Gantt chart, and this is basically an overview of kind of how we will separate the different tasks and try to stay on time with developing our product. And this will in turn help us to stay ahead of the curve. And I know that's also small on the printout. But as you can see, we will use our time very wisely and separating what we need to do, and we're going to try to have the final 2 weeks to just pretty much finalize the product and make sure we get our glitches out.
Cost is a very important part of this project. For this reason, we created a cost summary chart table which details each part of the product that we plan on buying at the current time, as well as its unit price, the quantity that we plan on buying of it, and the total price. For example, the Arduino board, we Googled it, and from a reliable website we found out that from there we can buy one Arduino board for about $55 approximately, as well as other things such as different sensors, which cost anywhere from a few dollars to about $20-$30, and in total we came out to be about $167, which meets our engineering requirement of the product should not exceed more than $250.
Let me also add to the cost summary table. When we made our cost summary table and we did the cost, basically we made sure that we would have enough money left over just in case if we have to buy any more extra components. Just in case as we're putting it together, we realize that we need more stuff. So we try to make sure that it was a reasonable amount of money so that we would have enough left over for anything extra. Now to conclude this presentation, basically from our motivation, we stated that we want to create a system that will detect the malfunctions and a programmable thermostat on HVAC systems. And we also want it to be programmable for the user so that the user can detect when it's on, when it's not supposed to be on. Also, we want the device to be user-friendly, and we also said that we wanted to alert the user when there are malfunctions. Also, from this project, it can reduce energy and pollution, and in the end, the customer saves money. Question?
Thank you. Very good. I really appreciate it. Just as feedback for your next presentation, you have terms like economizer and programmable thermostat, things like that. put them in a glossary at the end of your presentation. So if someone doesn't know what that term is, they can go look that up. You quoted some statistics about how many users have systems that operate differently than they anticipated or expected, leading to wasted energy. That is an awesome statistic. So I don't know if you have solid data on that, but that's really good to have in the future, if you need to respond to that. There was a statement, I think, Cameron, you made about the interfaces where there would be a Wi-Fi interface and a GSM interface. Are you anticipating using both?
We might use the Wi-Fi to communicate the one main board with the smaller boards to communicate. We might just use the GSM because the customer wants a text message. So
Okay.
we're looking into that.
Very good point. And what you're talking about is something that didn't get presented today, but I know that we've talked about it. You should probably find a slide where you can talk about the fact that having that one gateway node and then the other local nodes is something that you might want to implement in the future. So that's a good point, though. What's the analog design in your project? I know the programming, I know the digital part. What's the analog design?
You said it's gonna work for
No, it's just, so if you don't know right off the top of your head,
I mean,
then that's
no.
something that you really need to identify.
Okay.
Because one of the requirements for senior design is that it has to have that. So make sure that, oh yeah, why didn't we say that? That you have to build an interface between your sensors and the Arduino, for example, or a charging circuit to charge your battery or whatever. Just make sure you're clear on it, because the other thing is you want to make sure it's part of the work breakdown. But all in all, you guys did a really, really good job, and I look forward to what we're going to do next semester. And one final comment is I would encourage you to take some time for the remainder of this week to tell me what needs to be ordered, so that it's waiting for you when you come back January 6th, instead of we order it on January 6th, and then the 20th, it's finally here and you can go. All right?
Okay, well, you can take